This is video 9.4, Real Numbers. Before we move on to the problems, let's go back and review some vocabulary. To start, there was a point when you learned about whole numbers. Okay? Numbers were numbers that represented a whole, like 0, 1, 2, 3, 4, and so on. These were numbers that were not fractional. So for instance, 1/2 would not be a whole number. Then you learned about the opposites of whole numbers, or what we call integers, which are the whole numbers and their opposites. So they start to include -1, -2, -3, and so on. So integers include whole numbers and their opposites. The next level is what we called rational numbers. Now notice the number ratio is in here, and we write a ratio as, or like A over B. So 1/2 would be a rational number. 0.3 repeating would be a rational number because I can write it as 1/3. So any number that can be written in the form of like a ratio or a rational number would be considered a rational number. So for instance, 0.27 repeating is a rational number because it can be written as 3/11. In fact, any decimal that repeats or has a pattern, repeating pattern, or terminates, is considered a rational number. Now, whole numbers and integers are also rational numbers because they can be written as like -1/1 or 3/1. So it's possible to write any of these numbers as a rational number or in the form of A over B. So now let's make a diagram. Let's say I start with the category of whole numbers. Okay, this is where we said 0, 1, 2, 3, anything that represented a whole. Then with a category that includes all the whole numbers is the whole numbers and their opposites, or what we called integers. So now we started to add things like -1, -2, and -3. Those were considered integers. The next level, so what we just talked about, was what we called our rational numbers. Now, rational numbers were anything that could be written in the form of A over B, so like 1/3 or 0.3 repeating, 1/2, right? Now what we didn't talk about is square roots. Now, anything that's a perfect square, like the square root of 9, can be written as a whole number, right? Well, the square root of 9 could also be -3 times -3, so it kind of fits in lots of categories. So that is also considered to fit into this category. Now, there's another group of numbers which we call irrational numbers. And these are numbers that cannot be written in the form A over B. So an example of that might be pi. Pi is a decimal that neither repeats nor terminates, right? any square root that is not a perfect square would be considered an irrational number. So for instance, if I take the square root of 2 and I put it in my calculator, it comes out as 1.414213567, and it goes on and on and on with no pattern, no termination. So the square root of 5, not a perfect square, so it's an irrational number. Square root of 7, not a perfect square, an irrational number. Now, if I take all the rational numbers and all the irrational numbers and put them together as one category, I can call those real numbers. Okay? Now, there's also another group of numbers that you don't run across very much, which we call imaginary numbers. Now let's think about what might be in an imaginary number. Okay? Imaginary numbers don't fit into any of those categories, and they're numbers like the square root of -2. Now why would that be imaginary? Well, for it to be a square root, it needs to be something times itself. Well, 2 times 2 would not be -2. And in fact, -2 times -2 would not be -2, because a negative times a negative is a positive. So we call this an imaginary number. So these are our categories of numbers. And for this lesson, we're going to focus on what we called our rational numbers. So we're looking for any number that can be written in the form a over b, and we want to identify whether the number is rational or not. Right? Let's look at our first example, 1 over 7. Well, this one's easy because it's already in the form a over b, so we can call this number rational. Right? This one's a little more difficult. Now, if you remember, I said any decimal that repeats or terminates is considered a rational number. Let's think about why this might be so. This could be written as 1 4/33, or, if I want to write it in rational form, 37 over 33. So this would be a rational number. And I know this because any decimal that repeats with a pattern or terminates is a rational number. It can be written in this form, a over b. Now this one's a little tricky, and I want you to be really careful when you come across numbers like this. The opposite of the square root of 8 over 2. Now I'm going to use one of the principles I learned about in the other video, and I'm going to separate this out and turn it into the square root of 8 over the square root of 2. And I'm looking for the opposite of this. Now, I'm going to simplify this before I make a decision about whether this is irrational or rational. I'm going to factor it out. So this would be the opposite of 2 times 2 times 2 over the square root of 2. Notice this is the inverse of square rooting, so I end up with the opposite of 2 times the square root of 2 over the square root of 2. Now, notice that I have the square root of 2 over the square root of 2. That would have to equal 1. So these cancel out, and I'm left with the opposite of 2, or -2. Well, actually I can write that as a rational number, so this number here would in fact be a rational number. So make sure you simplify it before you make a decision as to whether something's rational or irrational. Now there's some examples here for you to try on your own, and this is the end of the video on real numbers.